All right, we are picking up where we stopped last time, I think. I think this is going to be 20 page, start on page 24 here. All right, let me get my head put on correct. Okay, suppose the reaction system UO2 solid plus HF gas produces UF4 gas and H2O gas. So as I read through that, I do notice that there's a solid in here. Let's take a second and I want you to write the equilibrium expression for this reaction. Take a second, over in the corner, write the equilibrium expression for this reaction. Right? Pause the video if you need to. All right, so the equilibrium expression would have these products, H2O squared times UHF4. Both of those are gases, so they both appear on top as products. And then in the reactants in the bottom, we'd have HF to the fourth. And then this UO2 solid, what happens with solids, they do not get included in the equilibrium expression because solids are zero order. Anything to the zero power becomes a 1. So the solid is not included in the equilibrium expression. A different way of saying that is the solid does not impact equilibrium. So in 1a, okay, I will finish reading that sentence. We spent a lot of time on the reaction. That was the reaction. And then after that, after the water, it says that the reaction has already reached equilibrium. So it's already at equilibrium. We already have products over reactants. It's in balance. Predict the effect that each of the following changes will have on the equilibrium. So somebody's going to change something. How is that going to be impacting things? Tell whether the equilibrium will shift to the right or left or not be affected. So when they make these changes, it's not at equilibrium. It's no longer K. It is then Q. And how is it going to shift? How is it going to react to get back to equilibrium? Additional O2 uranium oxide is added. So in the equilibrium expression, there is no uranium oxide. It has no effect on the system. So it won't impact the equilibrium. All right. The reaction is performed in a glass reaction vessel, and HF attacks and reacts with the glass. That means that the HF is going to be going away. Well, if we lose the reactant, we're not going to be at equilibrium. The HF is gone, so the reaction is going to shift to reproduce the HF. Because in order for it to be equilibrium, it's got to be products over HF, the reactant. With the HF gone, the reaction shifts and reproduces that HF, so it's going to shift to the reactant side or the left. What if the water vapor is removed? This is C. If the water vapor is removed, then we don't have enough up on the product side. So to get back to equilibrium, it's going to go back towards the right and make both products until we get to equilibrium again. I want to be clear, we get back to equilibrium doesn't mean that those two values get back to the same thing they were a minute ago, but that the product of the that when you multiply the products divided by the reactants, you should get back to K. Alrighty. All right. Number 2, an important reaction in commercial production of hydrogen. This is a gas, that's a gas, that's a gas, they're all gases this time. All the coefficients are 1. There'll be products over reactants with a whole bunch of first order reactants and products. How the systems shift in each case. See, carbon dioxide is removed, so we have fewer products, so it's going to shift to the right to replace the products. Water vapor is added, we'll have too many reactants, it's going to shift to the right to get rid of those extra reactants. In a rigid container, the pressure is increased by adding helium. Helium is not a part of this container at all. The reaction is not going to shift in either direction because helium is an inert gas and has no impact. The temperature is increased. And then it says real slyly that this reaction is exothermic. So typically this reaction is exothermic and it gives off heat. Typically, this reaction is exothermic and it gives off heat. If someone increases the temperature, it's not going to be able to give off that heat, and it's going to push the reaction back to the left. Oftentimes, when I see the reaction as exothermic or endothermic, I will write the word heat in the reaction. Now, if this is exothermic, I think of that as giving it off as a product, so I would write heat as a product. If it's an endothermic, I write heat as a reactant. And when they increase the temperature, that's like they're adding more heat, and adding more heat is going to shift away from whichever side has the reactant or product. And we go to E. The pressure is increased by decreasing the volume. So typically when we're doing pressure and volume, we look at the moles. If the volume is decreasing, it'll go to the smaller side of moles. If the volume is increasing, it'll go to the larger side of moles. And when I say moles, I mean we look at these coefficients and we add them together. We have 1 mole of CO or 1 mole of H2O. That's 2 moles of gas on the reactants. We have 1 mole of hydrogen and 1 mole of CO2. That's 2 moles of gas for the products. So the reactants and the products have equal moles of gas, so they're impacted the exact same. So we're not going to observe a change because both sides are going to change equally. All right, number 3, in which direction will the position be shifted based on the following changes? Again, everything's a gas, there's no solids. If H2 is added, we're adding extra products. We're going to have too much product when they add H2. So it's going to shift to the left to get rid of this extra product. I2 is removed. I2 is a product, so by removing it, the product side is going to be a little bit light, and it's going to shift to replace the missing product. HI is removed. With the HI being removed, it's going to shift to the left and replace that missing HI. Number 10, we've added something that doesn't react, and therefore we're not going to observe any change. E, the volume of the container is doubled. Again, we happen to have 2 moles on both sides, so no change. If the volume is doubled, typically it would go to the larger side because the volume's getting bigger. But since both sides have 2 and 2, neither side is favored. And the temperature is decreased, and it says this reaction is exothermic. So again, if this reaction is exothermic, then the products would be on the heat would be on the product side. So decreasing the temperature would shift it to the right. All right. Number 4, smelling salts consist of ammonium carbonate. The reaction for this decomposition is NH4 breaks down It is an endothermic reaction. If it's endothermic, that means heat is a reactant. You put heat in. Would the smell of ammonia increase or decrease if the temperature is increased? You add more energy in, add more heat, it's going to shift to the right. So the amount of ammonia is going to increase. So warming up your smelling salts will make them break down faster. All right, so we have a long question, and we have our answers down here. Suppose I was in butane producing isobutane and back and forth. Equilibrium constant appears to be 2.5. Suppose you have 0.01 moles of pure N-butane placed in a container 1 liter, 25 degrees Celsius. Write the expression. This is just going to be an expression. It's just the setup of the products over the reactants. It says equilibrium constant with a little c for concentration. We just put the concentration of isobutane over the concentration of N-butane is equal to K. It's just the expression. It's just the setup. If it had said Kp, it would practically be the same thing, except these would be in parentheses and be the pressure of isobutene, parentheses, the pressure of N-butane. So you go to Kp. It's pretty much the same setup, it's just symbols look different. Calculate the initial pressure in the container when the N-butane is first introduced before the reaction starts. So we have moles, we have volume, we have temperature. We're supposed to solve for pressure. That's just a PV equals nRT question. Yeah. 0.24 atmospheres, moles, RT over P. The N-butane reacts until equilibrium is achieved. Calculate the total pressure in the container. Sorry, people out there making a little bit of noise, so I have to be louder in here. N-butane reacts until equilibrium is achieved. Calculate the total pressure at equilibrium. Let's see what we did here. So, a 1-to-1. So for every mole of N-butane lost, we make 1 mole of isobutane. So if we lose X, we gain X. So as the pressure of N-butane drops, the pressure of isobutane increases, and they balance each other out. So it doesn't change. It stays as 0.24. Calculate the molar concentration of each species at equilibrium. All right, let's see how we're solving this. So is it 1 liter? Oh, good. So we have a rice table. N-butane makes isobutane. This is the initial value of N-butane. There is no isobutane. We're going to lose N-butane. We're going to make isobutane. And so we have these at equilibrium. K is given as 2.5. So K equals X over 0.001 minus X. And we solve for X. Now this solving for X is actually a little bit more difficult than anything we would deal with at this point. Typically they'll give us a little bit more of a clue as to how to get the X value. Like they might say it decreases by 20% or something like that. So you know that X is 20% of 0.01, and then you know that this other X is that same value. The volume of the system is reduced to half its original volume. What will be the new concentrations? Since there's the same number of moles on each side, the change in volume will not shift to equilibrium. The concentration of both of them will double. Makes sense? And suppose that in another experiment, this is a new experiment, 0.01 mole sample of isobutane placed in vacuum container. So this one's the reverse. This one's the reverse. Interesting. Kind of the same idea. Plugging it in, solving for X, and moving on. Okay. For our next question, calculate the value of the equilibrium constant. We have 2 reactions that can, in fact, be added together. When we add equations together, their constants get multiplied together. So we take the constants and multiply them together. Now, we did have to do some algebraic flippity-dipping here. And the first reaction had to be flipped around, so it's O plus NO. And when we flip that around, the products and the reactants are switching spots. So that means that the K becomes inverted. So like you take the inverse of K. So it becomes 1 over 6.8 times 10 to the minus 49th, which is where this number here is coming from, 1.47 times 10 to the 48th. And I think the other reaction was also inverted. They were both flipped around. So we took the second K and we flipped it over. Then we take these two values for K and multiply them into each other, and we get the equilibrium constant for the reaction. This reaction heavily, heavily, heavily favors the products. All right. Number 2. Consider the decomposition of the compound C5H6O when 5.63 grams of the C5H6O was sealed in an otherwise empty container and heated to the pressure rose this value. Calculate the K, the Kp for this reaction. Okay, all right. I should have said Kp. Oh, using the mass, volume.
Can I please have a custodian with the mop and a bucket to the hallway next to the auxiliary gym? There's some food on the floor. Thank you so much, Carolina.
Sorry about that. Right beside some walkie-talkies.
Battery high.
Changing the mass to moles and R and T and divided by the volume, we get the pressure. This is the pressure of the C5H6O3. Plugging that into a rice table. It says the pressure in the flask gradually rose to 1.63 atmospheres and remained at that value. That is the total pressure in the flask. All of these things are in the same flask. So the pressure slowly goes from 0.76 to 1.63 as the reaction takes place. Let's look at our rice table very closely. We have the C5, the H6O3 at 0.766 atmospheres, and we have nothing for the other two because it was in a sealed empty container. As it reaches equilibrium, we lose some of the C5, we make some of the C2, we make triple the amount of CO. So at equilibrium, we have these in terms of X, and we know that these have to add together to be the total pressure. So we have like a little math problem here where we solve for X, and then we can plug in those X values back in and solve for the equilibrium. So X was C2H6, 3 times extra CO, and then it's going to be cubed, and then 0.766 minus X. So on the bottom, we do our math, we get a Kp there. All right, the gas arsine. That's a great name. Decomposed as follows. We have ASH3 gas, AS parentheses S. That means that the arsenic is a solid on the product side. Then the H2. Why is it important that the AS, the arsenic, is a solid? That's very important because it does not impact the equilibrium. It doesn't have a pressure. It's a solid. In the experiment at a certain temperature, pure ASH3 is placed in an empty, rigid container. It's empty, so that's the only thing in there. They're about to tell us the initial values at a pressure of 392 torr. After 48 hours in the flask, it observed there to be 488 torr. Calculate the equilibrium pressure. Looks like for some reason Mr. Shangra turned the torr into atmospheres. I'm not quite certain why, but he did, so we will. So he turned the 392 into atmosphere. We turned the 488 into atmospheres. That's the total. Kind of like the last problem. He then said at equilibrium, it would equal the total. solve for X, and then plugged it back in, and eventually solve for KP. All right. Sorry, I'm just starting to wear down. Number 4, we have iron that's aqueous. We have SCN that's called thiocyanate. And the thiocyanate's aqueous, making iron thiocyanate, which is aqueous. How will the equilibrium shift if water is added, doubling the volume? If we double the volume, let's see, it wouldn't change. Changes the molarity of everything. It's diluting the molarity of everything. It's going to have a bigger impact on the reactant side. This should actually say 2 times Q. Q is equal to 2 times the equilibrium constant right now. So we need to decrease the value or add shift left, get it back down. Aqueous silver nitrate is added. By the way, AgSCN is insoluble. By adding the silver nitrate, they're removing the SCN from the solution. Adding silver nitrate will remove the SCN from the solution, which means it won't be at equilibrium. It's going to have to shift left to get back to equilibrium because the SCN is missing from the left side. NaOH is added. Turns out that iron hydroxide is insoluble, so by adding the NaOH, the OH is going to bond with the Fe and remove the Fe from the solution. It is on the left side. If you're removing a reactant, the equilibrium will shift back to replace it. Iron nitrate is added. The nitrate doesn't appear to react with any of these things, but we were adding more iron ions. We add more iron plus 3 ions. It's going to shift to the right. It's too much reactants. All right, this is more of the same where the reaction shifts left or right based upon adding or subtracting. If you add a product, it shifts to the reactants. If you add a reactant, it shifts to the products. If you remove a product, it shifts to replace the missing stuff that's been removed. Alrighty, I think that's the end of this worksheet, so we're going to hit stop.